Hello, Dynamics students. Um, so this is our last section from the textbook, um, chapter 17, section 5. This is the section where we have more or less arbitrary planar motion. So it'll be general, translational, and rotational motion. So just general planar motion. And so the equations will be a little bit more complicated than in some of the other videos. Here might be a situation where you have a boat, maybe that's moving forward, and simultaneously a moment is being applied by the two tugboats, and then you'd want to figure out both the acceleration and motion of the center of mass, as well as determining the angular rotations induced by the tugboats. Okay, we're going to focus on getting the equations of motion. We've already seen them actually, but I'm going to redrive them yet again to really hopefully highlight where they come from so you can get them for yourself. And then we're going to apply them to some problems. We've got some friction problems, and so basically we're going to have some various no-slip conditions, and we're going to look to see how that how to handle I guess either slipping or no slipping. What do we do in that case? And then we'll have some various quizzes there as well. Okay, first question for a reading quiz. If a disk rolls on a rough surface without slipping, the acceleration of the center of gravity will blank, and the friction force will be blank. So if a disk rolling without slipping, well, we've already seen that condition back in chapter 16 with accelerations. So the answer for the first blank was the center of mass had an acceleration equal to r alpha. The new thing for this chapter is the forces. And so it says the friction force will be blank. So it's a rough surface. There's no slipping. So we know it can't be kinetic friction. So the only option is C. So we're going to have the center of mass accelerates at r alpha, and the friction force will be less than or equal to mu s times the normal force. Remember, you don't know a formula for the friction force for static friction, usually. You only know that it must be less than or equal to mu s times the normal force. Question 2. If a rigid body experiences general plane motion, the sum of the moments of external forces acting on the body about any point P is equal to A, IP alpha, B, IP alpha plus MA, C, MA, or D, IP alpha plus R G relative to P cross M times A of P. Well, so C has the wrong units. B is a mix that has bad units anyways. You can't add things with different units. So the only possible option would be A or D. A is what we had last time when the center of mass, or sorry, when there was no acceleration. And so about point P. Today, when we have an acceleration about point P, the answer is going to be D. Now you might notice it's in a different font. That's because I had to fix a mistake in the slide. So we'll go through the derivation again, but you have to be really careful about the labels here. So I'm going to write it out with kind of full vector notation when I derive it, but pay close attention. It's really, really important. Okay. I don't think I have to really give you all the applications here, but this is because this is the point in the semester where we're pulling everything together. So you're trying to connect forces and moments with the actual motions and rotations that objects have. Okay. Here's a kind of typical sort of problem you might have. You're pushing down on this diagonal, you're given some angles and a radius of this or that, and they want to know what is the acceleration and what is the angular acceleration. And that may not have just a one-line answer. There might be cases, okay? It might depend upon the details of friction or static or kinetic or how you're pushing it. All sorts of things could start to matter. Another sort of thing, you're sitting in a car. Let's see. I was going to give Emily a hard time, but she's not in this class. So anyway, you're in a car. You slam on the brakes. Yes, you come to a stop. So that means you have horizontal acceleration. But you all know, at least if you're wearing a seatbelt, that you feel a rotation. Your head rotates forward relative to the rest of your body or to your hips. That's why you smack your face on the steering wheel. So that's the kind of thing that we have in mind, figuring out a combined translational and rotational problem. Okay, so they're just trying to set up the general formula. I'm going to rederive. They give us this equation, and this is fine. I'm going to rederive these and kind of show where they come from. We have kind of at least three standard ways to write this third equation. So I'm going to kind of go through that now. I just want to point out, when you sum the forces, that gives you the acceleration of the center of mass. Okay, watch the labels. It's really important that you do that. Okay, I'm going to switch screen, or actually I'm going to insert a slide here, and let's go through the derivation. It's important to know. Get rid of all these little boxes. I just want a blank slide. Okay, so let's go through the derivation for the moment equation yet again. I know we've done it twice, but let's do it again. Oh, hold on before I get going. Copy. All right. So what we're going to have is a situation where we have an axis, or well, we're going to have a point A. I usually say axis of rotation, but it's really just a point we're summing moments about. Okay, but I'm going to go ahead and draw that in. We'll change colors here. Okay, some point A. Oh, we're going to use capital A for that. And then we're going to have a rigid body. We're going to have a point in the body. And let's label that with a label I. That labels the, so that little circle has mass mi, and it has a perpendicular distance, which is all we really care about. You know what? Tell you what, a better way to write this, why don't we just say this? Well, this will be a bird's eye view looking down on top of it. And we'll say that A is going to be this point here. Okay, so here I've got this mass, mi, it has a vector relative to a, given by I/a, all right? Okay, so what we're after, well, really we want an equation describing the moment on this mass about point A. But first, we're going to focus on the little mass labeled with I, and then we'll sum over all the little masses to get the combined result for the whole object. So I write down, well, first I'm going to start with Newton's laws. So I would say F of I, F net on I, equals the mass times the acceleration of little mass I. Now, this would have both internal and external forces in general. We already know that when you sum over the entire object, the forces act on it to give you the motion of the center of mass. So I'm not worried about the center of mass motion. I want the rotational stuff. So I wanted to get a moment equation. So I'm going to take the cross product of both sides of this with Ri relative to A. Cross Fi, that becomes Mi times Ri relative to A cross the acceleration of mass I. So I've used Newton's laws. I'm just taking a cross product with the same vector on both sides. Next, we're going to use the relative acceleration equation. So let's write that down in case we don't remember. Remember, I can relate the accelerations of any point, any one point, to any other point. And I can say that the acceleration of I is the acceleration of point A, and then I would have plus alpha cross the relative vector from A to I minus omega squared Ri relative to A. Let me put in my unit vectors, or my vector labels. We're going to substitute that into here. Okay, when we do that, I'm going to add a new slide here because it's, where are we? There. Let's add a new slide. So we're going to need to know, so if you look at this slide above, I need to know Ri relative to A cross all this stuff on the right-hand side. So let's write that down. Ri relative to A cross the acceleration of I equals Ri relative to A. Yeah, I should be more careful with my labels here. Cross A plus alpha cross R A minus omega squared Ri relative to A. Okay, all I've done is substitute in for this quantity. Now, so I'm going to distribute the cross product. And when I take the cross product of the R vector with this third term, it's just going to give 0. So that one's going to drop out. So I'm left with Ri relative to A cross Ri relative to A cross alpha cross Ri relative to A. Oh dear. I got ahead of myself here, I think. There are two terms. I don't know what I'm thinking. Let's try that one more time. It would be this first two terms. This would be cross AA. Watch the labels here. Now I can write what I was going to try to write. A cross alpha cross Ri relative to A. This term I'm going to just leave put. This term I'm going to use the vector triple product formula. I've used it several times so far. This equals, so A cross B cross C equals back cab. So it's B, the middle one, is alpha times the dot product of A with C. That's going to be the magnitude of Ri relative to alpha squared minus Ri relative to alpha times alpha dotted with Ri relative to alpha. This last term is 0 because alpha is perpendicular to R. So this term is 0. So this one survives. So I find the following. Ri relative to A cross AI equals Ri relative to A cross AA. Remember, that's the axis. That's A, capital A is the point where we are applying or summing the moments about. So it's the acceleration of that point cross the relative vector plus alpha times the magnitude of Ri relative to A squared. Everything else was 0. Now if I go back, I've got a new form for this thing. I want to multiply by the mass and set it equal to the left-hand side. So I'll say Ri relative to A cross force on I equals Ri relative to A cross the acceleration of point A plus alpha times the magnitude Ri relative to A squared. Now we sum the moments, and then that's just going to give us the moments about point A. And I know it's about point A because it was all the vectors went back to A. And the internal moments cancel, and you're just left with the external forces that give rise to external moments. Equals, well, if I sum this is going to give me sum over Ri relative to A cross A plus alpha times the sum over I. Oh, I forgot to multiply by mass up here. Everything was times mass mi. So I'll have an mi here. Mi Ri relative to A magnitude squared. Okay. This term, so that's a sum of vectors weighted by mass. So basically what I can do is multiply and divide by mass here on this term. And then the denominator pairs up with the thing in parentheses to give me just the center of mass position relative to A, because everything's kind of going back, reference back to A. So this is going to give me the following result. I get the moment about A A is some arbitrary point, equals the mass of the whole object times the position vector from A to the center of mass cross the acceleration of point A. And then this factor right here is nothing other than the moment of inertia about point A. Okay, so this is our first equation, and this is a general equation. I've made no assumptions about where A was. It could have been on the object, it could have been somewhere, rigid, just anything rigidly connected, I guess, to it. Okay, so this is our first equation. Okay, so box that in. Watch the labels. This is the moment about A, is R from A to G cross the acceleration of A plus alpha times the moment of inertia around A. All right? So, and that's true for any sort of general motion. I've made no assumptions on that. If I take this equation, I still have general motion, but I apply this formula to the special case where A, point A, happens to be the center of mass, then this relative vector is 0, and I get the following. Again, for any general planar motion, I get the sum of the moments about the center of mass equals I about the center of mass times alpha. That's always true. It may not be useful, but it is always true. Box that in. The last thing I want to do is rewrite this equation, not using the acceleration of A, but instead using the acceleration of the center of mass. Okay, so I'm going to take this equation, I'm going to rewrite it using the acceleration of the center of mass, and I'll just be left with whatever I get. So for that, I want to start with sum of the moments about A equals mass times R G relative to A cross the acceleration of A plus alpha, sorry, I'm going to write it as I about A times alpha. They'll be really careful. I can't emphasize strongly enough. Be really careful with the subscripts. Okay, it's really just a game of subscripts, being careful. Okay. Now I use the fact that I can write the acceleration of A equals the acceleration of G using plus, just using our relative acceleration formula, alpha cross the vector from G to A. Notice up above I had A to G, now I have G to A. You just have to really watch that. Minus omega squared R A relative to G. And then if I want, I can, if I reverse the labels, I can pick up a minus sign. So I can write this as A G plus minus alpha cross RGA plus omega squared RG relative to A. Okay. So the plan is to take this formula and then this equation and plug all this stuff into here and then rearrange. So let's do that. So I'm going to get the sum of the moments. Oh, let's go back to black here. Sum of the moments about point A equals R of G relative to A cross all that stuff in parentheses, all this stuff. So it's AG minus, there's a minus sign here, alpha. Okay. I'm going to get AG minus alpha cross RGA plus omega squared RGA so that I've substituted in, and I still have this plus IA alpha. All right, let's clean this up. I have to distribute this cross product across all three factors. When I do that, this piece, when it distributes over here and it hits this one, it's going to give 0 because those are parallel. It's the same vector, so they're parallel terms. You take the cross product, parallel factors. When you take the cross product, you get 0. So this one is going to give no result. And I'm going to end up using the triple product again on this one, but let's go ahead and work that out. So I would get this equals R G relative to A cross AG minus RG relative to A cross alpha cross RG relative to A plus IA times alpha. Now, I'm going to use a triple product again. So I'm going to get A cross quantity B cross C is B, which would be the middle factor, times the dot product of the first and last, minus the dot product of alpha with R, and that's going to be 0 because of perpendicularity. So in fact, I can write this as RG relative to A cross AG minus alpha times the magnitude of R G relative to A squared plus something that goes away, and then I have this I alpha term. We're almost done. Now, these last two terms are proportional to alpha, and in fact, the parallel axis theorem tells us that IA equals IG plus the relative vector from of G relative to A, magnitude squared times the mass. I think I forgot my mass term. Oh, son of a gun. I forgot to multiply everything by mass. Let me go back and fix it. Oh dear. Oh, I lost it way back there, didn't I? Okay, every acceleration has to have oh, these were fine because that was there. Here, this was supposed to be a mass. This should have a mass. This should have a mass. This should have a mass and a mass. IG mass. Okay, so this is our formula. And when I look at this equation, now I can see that these just combine to give me I G, because IG is the difference between IA and M times the radius squared. That's what I have here, IA, and I have minus the radius squared. So this term gives rise to IG, these two terms. So I'm left with the following equation for the summing the moments about an arbitrary point A. That's going to be R G relative to A times cross the acceleration of G plus I G alpha. And that's a third equation that is true when you have general planar motion. So we have three equations. I'll write them here on one last slide here. And they all kind of look the same, or at least two of them look a whole lot alike. They just differ with labels. Okay, so let's be really careful. What are, for general planar motion, what are the equations which are true? First of all, the one that is simplest says that if you sum the moments about the center of mass, that just equals the moment of inertia about the center of mass times alpha. Clean, simple. That's kind of version one, moment equation one, but it only applies around the center of mass. If you sum the moments about some other point, A, you pick up an acceleration contribution. The first way, which is actually the way it kind of naturally fell out of the derivation, was that this equals the mass times R GA cross the acceleration of A plus IA alpha. And sure enough, if you substitute A equals G, then this relative vector is 0 and A is G, they're the same, no problem. The other equation that I just went through up here is very similar looking, but watch the labels. This other way said that the sum of the moments about point A, which is arbitrary, is the mass times RG relative to A cross the acceleration of G plus IG alpha. And you can check if you substitute in A equals G, then again, this relative vector is 0 and you get the right answer. So there are three versions. These last two look so similar, but the labels are different. And they both refer to the moments about the same point. So don't mess that up. Just be careful. Use one or the other. On the quiz, what they did is they kind of took one term from one version and the other term from the other one, and they had a mistake. So, anyways, remember that, and we'll use that in the rest of this video. Okay, let's continue with our presentation. Having done all that, hopefully now you kind of see where everything comes from. And I will be honest, I don't do enough of these problems to just write it down. And not, it's all a question of minus signs most of the time. So it's not so hard. I pretty much go through the derivation every time, and then I'm sure I understand where it comes from. It's not that hard. And it's, it's always the same set of steps. So, okay. Right. So here, they're working out the summing the moments about point P, and they say that you have so they're writing it using this. This is using these the center of gravity. Right, so just, okay. That's fine. So they're using the, right now they're using the third version. Okay, so here's a, so they're going to use the third version. Actually, sorry, take it back. They're using the first version. They're summing the moments about the center of mass, which just gives you the moment of inertia about the center of mass times alpha. So this is a wheel, it's rolling, and so they go through, they give us various diagrams. So we have three scalar equations. We have the x equation from Newton's second law. We have the y equation from Newton's second law. Then we have the moment equation about the center of mass they choose. There's no benefit. There's really only one moment equation, because if you know the moment equation about one point, if you're really patient, you can figure out it's equal to the moment equation from another point. So that gives us three scalar equations. But there are four unknowns, because there'd be a normal force, a friction force, a weight, and some pulling force. And you might say, well, wait a minute, don't we know that don't we know that alpha and the acceleration of the center mass are related, like we did it back in chapter 16? And I would say, not yet. We don't know that. We don't know that there's any relationship yet without specifying more. To really solve this, we have to say something about, does it slip or not? If it doesn't slip, then we can basically convert the acceleration into an alpha or vice versa. So the alpha and the acceleration are one and the same. If it does slip, then we have to use kinetic friction, and it will no longer be true that the acceleration of the center of the wheel is the same as alpha times r. When we said that these were equal, that required no slipping. So if you have kinetic friction, that's not true. So in general, you have to supply this extra equation, the kinetic friction equation. So then you would have four equations, four unknowns, and then it's just a bunch of algebra. Personally, I'd probably just put it on the computer and let it do the linear algebra and solve it. Okay. So what's our general procedure? You choose good coordinates as usual. Specify positive and minus signs. Work out the moment of inertia about whatever point is appropriate. So they wrote AG, and that, I guess that's fine. You don't have to do that. You could find the moment of inertia about some other point if you want, and you would use one of the versions of the moment equation, whatever's appropriate. Okay, so that is what we're going to do. Oh yeah, using the unknowns, that kind of stuff. Okay. Here's our first example. Okay, so this is there's a wheel. It's tied to the wall. There's some tension on here. And so you might say, oh, it's just going to rotate clockwise. But no, there is an external applied moment for this problem. And so, in fact, the moment is going to be so strong that it actually causes the wheel to, or it causes the string to wind up. And if you think about it, as the string winds up, the wheel is actually going to slide backwards. It's kind of like, I don't know, maybe you guys are a little young, but Michael Jackson doing the moonwalk is the idea. So you're rolling forward, but you're moving backwards. All right. They tell us the mass of the spool is 200 kilograms. The radius of gyration They don't give us the moment of inertia. They say the radius of gyration is 0.3. Okay, we won't be fooled by that. We can figure it out. And the coefficient of kinetic friction is 0.1, so it's really low. That's just a shade more than ice, maybe. Maybe it's like ice with scratch marks or something. Okay, and okay, so we want to go through, follow our plan to solve this one. So we want to have a good diagram, draw good free body diagrams, think through what are the relationships between angular acceleration and any acceleration that might be there. Okay, think that through. All right. In fact, we can talk about that now. There is slipping in this problem because as the string is wound up at this bottom contact point, it's actually going to have sliding to the right. So even though alpha is positive, the acceleration is going to be, sorry, alpha is positive and the acceleration is going to be positive. And because they're slipping, there will be no general relationship between the tangential motion at the contact point with the motion of the center of mass. However, there will be no slipping at point A. So we're going to have slipping at the bottom, but we will have no slipping at point A. So we can use the kind of familiar no slipping condition, but we have to make sure to only use the radius for point A, not the radius all the way down to the point of contact. So we want to use the 0.4 number, not the 0.6 number. That's kind of the, to be honest, that's I think the trickiest thing in the whole problem. All right, let's solve this one. So let's draw a free body diagram. I'm going to do this one. I think I want to do this one symbolically. Okay, so in this one, we have a wheel, we have a surface, we have another circle. The rope is attached here, and it pulls that way. And let's write our numbers down. And we have an external moment equal to 450 newtons. And I'm going to say the radius for the outer radius, I'll do with capital letters. That'll be 0.6 meters. The inner radius we'll make that smaller. We'll make that 0.4 meters. They tell us, let's see, they tell us mu k equals 0.4, and they tell us the radius of gyration we should read that carefully. Radius of gyration about the center of mass is 0.3. So they tell us the radius of gyration about the center of mass is 0.3. All right, 0.3 meters. And that will immediately tell us that the moment of inertia will equal the mass times the radius of gyration about point g squared. So we know the mass. We can get these numbers. Oh, because the mass is 200 kilograms. I think those are all the numbers we are given. Very good. So let's draw a free body diagram here. We have a weight going down. We have a tension force going that way to the right. We have friction, which is actually going to, well, it tries to impede the rotation. So friction is going to go there. It's going to be kinetic friction. And then I also have a normal force. So there are 4 forces which act on this system. I can write, okay. the other thing I know is no slipping at the top. So if there's no slipping at the top, we know that the acceleration of the center of mass is going to equal little r times alpha. Little r is the radius to the inner circle. I cannot use no slipping condition at the bottom because it's got kinetic friction. It does slip. All right. Most of the rest of the problem is just an exercise in arithmetic and algebra. So let's apply, let's add up the forces in the y direction. That's going to be, well, in the y direction, I have a normal force minus mg equals 0 because there's no acceleration up and down, which tells me that the normal force equals mg, which immediately tells me that the friction force, because it's kinetic, is mu k times mg, because the normal force equals mg. All right, let's go to the next page. So now I want to sum the forces in the x direction. So I have a tension to the right, I have friction to the left, and that's all. So that must equal the mass times the acceleration in the x direction. But this, I know, equals little r times alpha. And let's just double check our minus signs here. If alpha is positive, so counterclockwise, then the string will shorten, which means the acceleration is positive. So it's a plus r alpha, positive r times alpha. So I can write this out as tension minus mu k mg equals positive r alpha. And then I have my moment equation. And I'm going to sum moments about the center of mass. So then I can just say that the sum of moments, so I'm using, going back, going up here to this slide, I'm going to use this first version of the moment equation. And say that that equals I g times alpha. So I look at my diagram and I sum the moments. I get a moment from the tension and I get a moment from the friction force. The moment from the tension is negative and the moment from the friction force is negative. Ah, I forgot something. I was about ready to make a mistake. And I also have this external moment applied from the outside, which is a positive moment. So the moment equation is going to say we'll just call it capital M. So I get the external moment minus the moment from the tension. So that's going to be little r times T minus the moment from friction, which is big R times mu K times mg. So that's the friction force. That equals I alpha. All right. We know the radii, we know mu, we know m, we know g. We know the external moment, we know the radii. So the only, let's underline our unknowns now. We've made enough assumptions, we can do this. So my unknowns are tension and alpha. Tension and alpha. So I have to solve these two equations. So what I'm going to do is rewrite this one first and say tension equals R alpha plus mu K mg. And then we're going to, see, we're going to substitute that into here. And then rearrange and solve for alpha. So doing that, I get that the moment, the external moment, minus R times mu K mg minus R times the tension, which is mu K mg plus m little r alpha, which equals I alpha. So next up, I need to algebraically move this across and then regroup. So looking at that, I end up with external moment minus big R plus little r times mu K mg divided by m r squared plus I equals alpha. Very good. Let's type in some numbers. This is going to be 450 minus, if I add the two radii, you get 1 times 0.1 for mu times the mass, which was 200, times g, which is 9.81, divided by 200 smaller times the smaller radius, which was 0.4 squared, plus I. Oh, we never solved for I. I equals the mass times k squared, so that's going to be 200 times 0.3 squared is 18. If you type all that in, we get alpha equals, I'm getting 3.17 radians per second squared. And last up, they want us to also solve for the tension. I go back to my force equation is probably the easiest, and I can say tension equals force of friction plus mr alpha mu k mg plus mr alpha. Plug in all our numbers, and I'm getting 450 newtons as a result. Okay, so hopefully that was okay. Let's see how we did. Now they didn't do it symbolically. They did it with lots of little numbers, but that is 200 times g for the weight, so that makes sense. So solve for the y equation, you get the normal force, and then if they multiply that number times 0.1, they get a friction force there, and yeah, there's 18. That's I. That's what we had. The same answer. So it matches. All right. Here's a concept quiz. So if we look at this scenario, we notice that we have okay, they tell us it's a spool of some mass, and they tell us the radius of gyration. So basically the moment of inertia. And they tell us that alpha is oriented counterclockwise. And they're going to actually say that the numerical value of alpha is always positive. So they have to put an explicit minus sign in here. Okay, anyway. So we know alpha is clockwise. And you're pulling it, the external force is to the right. So, all right. They want to know if we can say anything about the friction force and the acceleration of the center of mass. And the options are the friction force should point to the right or to the left, and the center of mass should have an acceleration to the right or to the left. Well, let's think about that. Well, I'm not going to tell you the answer. Hold on. I'm going to ask you this first thing in class. So think about it. See what you get. A little bit tricky. And down here, similar kind of thing. You have a situation, the moment equation about G is given by what? This would be the force of friction at A. And just so the alphas here are absolute values of alpha. They're going to have, it's a positive quantity. So don't worry about the minus sign in front of these three alpha terms. Those are, let alpha be a positive quantity. And then the minus signs will be there to account for the arrow. All right, so I'm going to ask you which one of these is right next time. Talk to you later. Bye.